Now we will see what can be done with ions. In order to synthesize elements using an ion beam, the beam must have ions that are accelerated to about 0.1 of the speed of light. Only at this energy level can the Coulomb barrier be overcome, and can the two nuclei be forced to interact with each other in order to obtain a new formation, much like Rutherford did back in 1919. Before the war, Luis Alvarez, a famous American physicist from Berkeley, obtained several ions per minute of accelerated carbon at the Berkeley cyclotron in 1940 for the very first time. I know Luis Alvarez. We met in Stockholm in 1968. I even attended his Nobel Prize award ceremony. An interesting fact about Alvarez is that he is the inventor of the bubble chamber. He told me about how they used a bubble chamber to search for gold in the tomb of Khafre, the son of Khufu, known to the ancient Greeks as Cheops. In the second largest pyramid in the world, they were looking for gold, which was probably hidden in the body of this pyramid. For this purpose, they used a bubble chamber. I don't really know why a bubble chamber was needed here. One could do without a bubble chamber. Most likely, the bubble chamber was surrounded by position-sensitive spark chambers, and it is possible that cosmic muons were used, the intensity of which was quite sufficient at around 10 to the power of 4 per square meter per minute, which cut through the pyramid in order for coordinates to be recorded, and the absorption of muons were observed. At first, this installation was outside the pyramid, without walls. They looked at how cosmic muons registered from different angles, and after that, they placed the chamber there. And for 2 years, they were looking for these treasures of the son of Cheops. Unfortunately, they did not find anything. Of course, this was a demonstration experiment during which several ions were obtained, but I would like to highlight that these demo experiments go down in history as the first of their kind, and it does not mean anything that they only obtained a few ions per minute, while in today's time we can obtain 10 to the power of 13 or even 14 per second. The first to achieve this was Alvarez, albeit with his own low intensities. In fact, diverting a little from the pyramids and from the personality of Luis Alvarez, we must say that after the reactors, serious studies of nuclear reactions under the influence of heavy ions were undertaken in Berkeley at the Heavy Ion Linear Accelerator, as well as in Moscow at the Heavy Ions Cyclotron. I would say that these two laboratories were pioneers in the world, located on opposite ends of the globe, in Berkeley and in Dubna. The first experiments with heavy ions showed that as a result of the collision of two nuclei, a nucleus with a very high temperature can be obtained. The nucleus can be heated to a temperature of several mega-electron volt, which is more than 10 to the power of 10 Kelvin. It has shown that in tangential collisions and the capture of heavy projectiles, the nucleus will spin wildly, and the spin of this nucleus can be 66 to 70 H, maybe even 80. And it is shown that this nucleus can be deformed. We saw in spontaneously fissioning isomers that the nucleus can be stretched in such a way that its half-axis will be 3 to 1. Can you imagine? And despite that, it still survives. It became quite clear that heavy ions are excellent tools for studying nuclei in all these aspects. In extreme conditions, with high temperatures, with great rotation, and with great deformation. And then they began to build special heavy ion accelerators. And then national laboratories of heavy ions were built in the United States, France, Germany, Italy, and Japan. And then heavy ion colliders were built in Brookhaven, in CERN, and in Germany. And soon, we will have a heavy ion collider here in Dubna as well. And this direction of research has begun developing very rapidly and efficiently.